All right, so I wanted to look at this example here because they gave us a specific range for what x can be. Okay? It says here, a manufacturing company makes door hinges. They have a standing order filled by producing 50 each hour, but production of more than 150 per hour is useless, as they will not sell. So here they figured out a range. They know they got to make at least 50, but if they make more than 150, they're not going to sell those, so we don't want to make them. All right? The cost function for making X hinges per hour is this. All right, so you can see here, you know, they have $160 per hour in fixed costs, and then all this is related to the materials and labor. Okay? And it says, find the minimum and maximum hourly costs and the production levels when each occurs. Okay? So we want a minimum and maximum and our production level. Okay?
You said range. You said the 50 to 150 in range, but isn't that domain?
It is the domain of the function. I was just talking about a range of numbers, not the term range. But yeah, this was our domain that we're given for x.
So sometimes your step 2 is done for you.
Yeah, sometimes step 2 is done for you. They've given you the domain.
And this one's not going to have a diagram. So we skip step 1.
Yeah, we wouldn't really draw a picture for this one.
Okay, so step 3.
So, well, hang on. Step 2, part of that, though, was finding critical values. Okay? So we do want to find C prime and set it equal to 0 and figure out what critical values are. All right, so we have 0.0021x squared minus that'll be 3592, is that right? X. We double that, 1769 times 2, 12, carry the 1, 18, 1 is 19, carry the 1, 14, 15, carry the 1, and yeah, okay. So then plus 14.663.
Why?
That's our derivative of our cost function. Okay? So how do we figure out when this equals 0? Yeah.
Quadratic formula.
Yeah, we'd have to use quadratic formula, or if this is a calculator part, which it would probably be with those kinds of decimals, we could use the calculator. All right? If we're using the calculator to find the zeros, all right, we can graph this 0.0021x squared minus 0.3592x plus 14.663. Now, I'm going to set my window here because I know my window is going to be x between 50 and 150. So I'm going to set my window to have an x min at 50 and a x max at 150. And I have no idea what the numbers for y are going to be. So I'm going to set it to go from -10 to, let's say, 1,000. Okay?
Why -10?
It was there. You could make it 0 if you want. It doesn't matter. Okay? So now I hit graph.
I think it's still loading.
Well, maybe I set my window too far. Let's go -10 to 50. Maybe I zoomed out too far. Oh, yeah, I can see it. It's in there. So I need to, I'll do a zoom box this time. That'll make sure I get it all. Okay, so here, okay, so let's see here.
So you have to do when x equals 0.
Yeah, or not x equals 0, when this derivative, this is the graph of my derivative, it's a parabola,
Yeah, but how are you gonna find your zeros?
I'm going to zoom in here and look at where it crosses my x-axis. So the derivative is my 0. So I can come over here.
Yeah, so when the derivative crosses the x-axis.
Yes,
the
when the-
derivative is 0.
Yeah, when the derivative is 0. So second calculate, number 2 is my 0. So left bound is there, right bound is going to be there, and then a guess. Okay, so I know one of them is at 103.7. Okay, so x equals 103.7. And then I've got to do the same thing to find my other 0. Let's get over here. Okay. Oh, come on. Need to get to the left of this, and then I'm going to do second calculate. My 0, left bound is there, right bound we'll put there, and then a guess right there, and we see it's 67.3. Okay? So 67.3. If you got the quadratic formula, you get the same thing. Now, here's the deal. We've got values here where we can set up a sign diagram. Here's 67.3, and here's 103.7. Okay?
So you put 1 at 50 and 1 at 150, or no?
Well,
The words are combined.
50 and 150 are just going to be the ranges, or the ends of our domain. Okay? So those are the boundaries here that we're going to deal with. That's not going to affect our curvature for our graph. Okay, so I could still test this by plugging in a 0. Okay?
And you found the x values just by the places on the...
Yeah.
Wait, you can still test a 0? It doesn't have to be in between 50 and
Sure.
67?
Sure. These are just logical limitations in our situation. That's not going to affect the actual mathematical curve. It's just we're not going to want an answer at 0. But I can still plug in 0 and see, oh, my derivative is going to be positive to the left of 67.3.
Okay.
And if I plugged in something between these two, like 100, okay? If I plug in 100 squared would be 10,000. So times that is 21, minus about 36, so that's in the negatives, plus 14, so I better do it a little more carefully. 21 plus 14 would be 35.6 minus 35.9,
So it's negative.
so it's going to be negative. And then on the right-hand side of 103, I could plug in whatever, it's actually going to end up positive. All right? Since I had the graph here, by the way, notice I could have filled out my sign diagram just by looking at the graph too. The derivative is in the positives to the left of this 67.3. It's in the negatives between the two critical values. And it's positive once we get to the right of it. Okay? So you could have seen it that way as well. So, where's our minimum?
At 67. It's at 67. It's at 103.7.
Yeah, we're decreasing and increasing. That means this right here gives us a min. And right here,
Max.
this is going to be a max. Now, these are local mins and maxes.
What does that mean?
All right? That means we still need to test the endpoints. Okay? So, what we're going to do is
Wait, what endpoints?
the endpoints, 50 and 150. Because it's possible, check this out, it's possible that we're increasing, then decreasing, then increasing, our interval could go like this. Where, yes, this is a local max, but over here at 150 is actually higher than that local max. Okay, and same thing could happen with the min on the other side.
How do we know that by looking at it?
We don't know it by looking at it. What we'll do is we'll actually plug in these values. Okay? Now, the other thing we have to consider with this problem is the fact that you can't have 67.3 units. So we would need to check the integer values on either side. So I actually need to test a few different values. I'm going to test where x is 50. I'm going to try 67 and 68. I'm going to try 103 and 104. And then I'm going to try 150. I'll plug all of those into what we're trying to find the min and max of. That's our cost function. All right? So C of x. And this is where, remember, using the store function on the calculator is helpful? Okay? Check this out. All right, I'm going to quit this. I'm going to first of all do 50 and store that in x. And then I'm going to punch in my cost function. So 0.0007x to the third minus 0.1796 x squared.
How come you plugged numbers into the derivative for your sine graph, but now you're plugging in 50 and 150 into your original function?
It's because of what I'm looking for. On the sine graph, I was trying to determine where max and min points were.
Yeah, but then
So I need to determine increasing and decreasing.
but then you said that you have to test the integers for, like, if it says 67, 68, and 103, and 104, that doesn't affect your maximum point. Or does?
No, these are going to get, one of these is going to give me my max, and one of these is going to give me my min.
So what's the point of the sine graph?
Well, the sine graph, I mean,
Like, are we done with it? Now we're moving on?
we're done with the sine graph, yeah.
Yeah, I was confused. I thought
This
we were-
is kind of just out of habit.
Okay,
I mean-
I thought we were just adding more points to the sine graph.
Yeah, since we are going to just actually plug them in and evaluate all of them, the sine graph isn't absolutely necessary, no.
Okay.
But,
So they're never going to ask you for local maxes and mins. They want the real one.
well, that's the thing, yeah, and depending on your interval, it may be at one of the local max or mins, okay? So like here at 50, we get 531.65, so let's write that down. 531.65, okay? Then we want to do the same thing for 67, so I'm going to do 67 store x, and then go back to where I punched it in, and now it's 546.73. 546.73. Okay. Then I need to try 68. All right, so 68 store x. Go back to where I entered that in. It's 546.72. Okay, that's at 68. Then 103, same thing. $529.82. Okay, and then same thing 104. $529.8. And then 150. Okay, 150. 150, stow, X, 680.95.
So 680.5 is your, 680.95 is your max, but 67 point, I mean, but 103.7 is still your min.
Well, let's take a look, because again, we have to have integers, right? We have to have integers. So if we look at this graph, here's what we have. Okay? At 50, we're at 531. So let's say we're at 50, we're at 531. Let's say that's here. And then at 67, we've gone up. And 68, we're almost even. The min is like right, or the max point is like right there. Okay? So there's 67 and 68. Then we come over here to 103 and 104. And we're at 529. So that's lower than 50, where we were at 50, but just a little bit. Okay? So it actually has gone up. It's come down. All right? And then at 150, it's up here at 680. It's gone up quite a bit, actually. Okay? So, our minimum hourly costs are actually going to occur when we produce 104 hinges. Okay? Now, it's a min by 2 cents over producing 103, but still. Okay?
Okay, so that's why I have to test the integers.
Yeah, that's why we have to test the
So
integers.
it's like our new max is now 150.
Yeah, this is a case where the local max would have been here at 67, all right? But you look at the end of the interval, this 680 gives us the maximum within the domain that we're looking at, okay? So those are our maximum hourly costs, would be producing 150 of them. Our minimum hourly cost would be producing 104 of them, okay?